Energy 301 and ATS 564 students, it's time to start talking about statistical models. You know, we're in a class that on the energy side is called Modeling Electrical Load and Yield, and on the atmospheric science side is called Statistical Meteorology. It's probably not a terribly big surprise to find out that a big part of the theme of especially the second half of the course is statistical models. Now, gosh, literally the very first lecture in this course we had a kind of an overview of all the different ways we could have models, like physical models and dynamical models and computer models, and statistical models was on that list. And it was a hard term at that time to define, and I stand by that. You know, if you just Google define the statistical model, it quickly gets very technical very fast. This is not a small research issue as to what exactly constitutes a statistical model, but for our purposes here, we can say that a statistical model is a way of making predictions or understanding a system that uses data about past observations to produce estimates, or we could say forecasts, about future observations. Okay, we're going to use past performance of a system to tell us something about what's going to happen in the future. Suppose you needed to make a forecast, for example, of like the power production for some wind turbine. Okay, I could think that there would be a number of different ways we could do this. I mean, for example, maybe we could actually create some kind of dynamical model of the winds, where we actually took like the winds at that location, that wind turbine. We actually tried to compute them in a very dynamic kind of way. I mean, we would actually need to compute things like the pressure and the pressure gradient force and the pressure pattern around like a cyclones and anticyclones. You know, we talked about all those kind of forces that give rise to the winds back in Module 1. We could compute all of that. It's done. We could then maybe start having to think about the role of friction by computing things like the roughness of the surface, and the atmospheric science students can tell you all about aerodynamic roughness, length, and drag coefficients and so on that can be used to compute the friction acting on the wind, the production of turbulence, and the vertical transports of turbulence by eddy motions in the atmosphere. We could talk about the stability profile in the Earth's atmosphere near the surface, which talks about the atmosphere's ability to transport momentum from up above the windmill down to the height of the windmill. This could all be done. It just doesn't, I'm not sure we get all that great of a forecast of the wind at the height of the turbine over and above other ways that perhaps we could make estimates of the power that's being produced. I mean, there are other techniques that might work better. A technique that probably wouldn't work better is to make a physical model. Okay, you know what I mean by a physical model? I mean literally as in we built it out of plastic and sticks and popsicle sticks and glue or whatever. You know, make a little windmill and somehow like simulate the wind that would be going over it by, you know, with fans or something. I don't know that we could come up with any kind of improved understanding of how much power the windmill would be producing on any given day or whatever using a physical model. That's not really right tool for this particular job. But maybe the past performance of this turbine could actually tell us something about, we could estimate the power, what it will be producing now. For example, maybe we have observations of the wind at a wide range of you know, hours and days and months and years. We have all these observations of the wind and the wind power and so on. And, you know, maybe, for example, there's a strong seasonal cycle to the wind. Maybe it's windier in the winter at your location and less windy in the summer. Just having a simple understanding of you're trying to predict the amount of wind and therefore wind power in, say, August based on that seasonal cycle, that would be a type of statistical model. You are simulating the amount of wind and amount of power being produced based on historical data. You're saying, hey, I know that it's August. I know from past experience that I can simulate the annual cycle in this way. Okay, I can live with that. That's not a particularly sophisticated statistical model, that little composite like that, but I can live with that. For example, maybe there is a strong diurnal cycle to the winds. Most locations are much windier in the afternoon and much less windy in the overnight hours. You know, you could use the records of the winds and the wind power being produced by your turbine at each of the 24 hours of the day, and you could say, hey, if I'm trying to forecast the amount of wind and therefore the amount of wind power at 3 o'clock in the afternoon, I could just talk about I could be simulating or modeling the diurnal cycle of the winds just based on what was the average at 0Z and at 1Z and at 2Z on the clock and so on. Maybe. Again, that's a type of statistical model, not a particularly sophisticated one, but I could live with that. That could be part of the answer here. For that matter, maybe it's both. Maybe there's both an annual and a seasonal cycle to the winds at your location. For example, maybe there's a small diurnal cycle in the winter when the winds overall are weaker, let's just say, and in the summer the winds overall are stronger, and there's a stronger diurnal cycle to the winds. Okay, that certainly is, I can envision that there's parts of the world where that would be true, where there's both a changing annual cycle and a changing diurnal cycle, and you might have to simulate the wind by knowing those statistics, right? I mean, I want to make a forecast of the amount of wind power at 4 o'clock in the afternoon in the month of July, or at midnight in the month of February or something. I could envision that, okay? Forecasts of power production at a wind turbine certainly could be made that way. But, if we're just thinking about this in a more of a statistical kind of way, I mean, if power produced is going to be our random variable, well, we could use its correlation with another random variable to produce some estimates. So, for example, here I've got some data, obviously just made up data, that I have plotted on an XY type scatter plot, where on the x-axis I have an observation of pressure gradient. Now, pressure gradient, remember, is what gives rise to the pressure gradient force. It's how pressure is changing with respect to distance. It's one of the main forces that are responsible for the speed of the wind. It has units, well, you can express the units in a number of different ways. Just for sake of argument here, I labeled them as millibars per kilometer. Okay, how many millibars the pressure changes every kilometer. All right, and on my y-axis, I have what I'm hoping to forecast, which is the power produced. And again, we're going to work with just the SI unit of that. Let's just say watts, okay? It's arbitrary. We could have scaled it any number of different ways. Sorry, there's so much static down here in the basement. All right, we could be doing this. So here, when we have designed this experiment this way, the statistical experiment this way, using this historical data that we've plotted on the diagram here, our pressure gradient is going to be on our x-axis. It is our predictor, which we're going to make as our x variable. There's a certain number of realizations of x here, n of them, and each of them is a predictor of some value of y. Let's use a more technical term here in statistics. We're going to say that this makes x our independent variable. This is the thing we're not in any way in control of. We just measure this. I'm going to, in the future, when I'm trying to make predictions of the amount of power to be produced, I'm going to be given, here's the current pressure gradient, make an estimate of the power produced by my wind turbine. This is the independent variable. We're not in control of this. All right. Now, oh man, these are really stuck. Excuse me here. All right. Here, power produced is going to be on the y-axis. This is what is being estimated. Now, the right word for this in a statistical conversation when you talk about like correlation and best fit lines and so on is that this is the dependent variable. So the x is the independent variable, and the y, which you are trying to make your forecast, this is your predictand, this is what you are trying to predict, this is what you're trying to estimate, is your dependent variable. It depends on the other variable. The power produced is going to be depending on the pressure gradient. Now we have this best fit line that we are going to produce that goes through that data that is going to have certain properties, as we discussed last time. Like it's going to have the smallest possible value of the sum of the squares of the residuals and all that kind of stuff. And there's a couple of different ways we could write such a thing. We could say that y hat, our estimates of y at time I, our ith observation of y, or our ith estimate anyway of y, would just be this b naught plus b1 times our xi. Whatever our value of x is at this time, we can use our regression parameters b1 and b naught to come up with an estimate y hat of I. Or we could actually write this out more like we did in question 3, if you remember that, where we had like y of I, the actual value that happened of y, is equal to our estimate of y hat, which is b naught plus b1 times xi, plus this little residual or error, epsilon. Epsilon of I. Every one of them is different. Now, there's two terms there, that beta naught, and I'm sorry, B naught, and that B1. The first part, B naught, that is the intercept. That is the y-intercept of that best fit line there. It's going to have units that are the same as the units of whatever your units of y are. So in this case, B naught is going to have units of watts. Okay. Now, our second regression statistic there, B1, is the slope of the regression line, and it's going to have units that are the ratio of the units of y over the units of x. So in this case, it would have rather horrible units of watts over millibars per kilometer, but whatever they are, they are. Now, it would be easier to envision what we're talking about with those units if we said, let's just keep the same graph, but let's pretend it's something else. I'm going to change the x-axis to a time, like years, okay, where like maybe this is the average annual global temperature, and on the x-axis is years, and on the y-axis is the global average temperature in degrees Celsius. Well, then that slope of that regression line would, or that best fit line, if you would then have units of the y-axis divided by the units of the x-axis, so degrees Celsius per year. Oh, I get it. A degrees Celsius per year of that for that unit, that's a trend. Okay, that's saying how much this object, this parameter that we're predicting, how much it changes per year. Okay, so like that would be, now we can multiply that by 100 to make it degrees Celsius per century or something like that. I mean, degrees Celsius per year might not be the best unit for such a thing. Now, whenever you are computing the estimates that come from this correlation line, from this best, I'm sorry, from this correlation line, this best fit line, there are going to be, you're going to be getting these estimates like y hat of I, okay, y hat 1, y hat 2, and so on. And there's actually going to be ways that you're going to be able to estimate the size of the residuals, or the errors, as some people would call them here, where you could kind of think of it as having like a little box and whiskers type diagram around each of those estimates. There's an estimate of y hat, that is actually on the regression line, the best fit line there, at each value of x of I, and then there's some range that the answer will have some probability, the real value has some probability of falling in that range, typically like 95%. There's a 95% chance that the real value y of I is in the range y hat of I, plus or minus some interval. We're not going to get bogged down in how to produce, I mean, good grief. My linear regression and models textbook from when I was a stats major is literally 1,200 pages long. We aren't going to learn all of these techniques, but the idea that you can put some kind of estimate on the errors or the residuals, and notice then that, like, for example, the one they have highlighted with a star actually falls outside of the estimated range and so on, but that's okay. 95% of the time it will fall within that estimated range and so on. That's a standard statistical technique, and if you needed that in your job, it would be a relatively small thing to find out what the octave command to make that work would be. Now, notice this particular statistical model that we created here is just a line. Okay? All we have said here is we've created a statistical model where we can make forecasts of y hat, just based on a linear dependence on x. As x increases, y increases. As x decreases, y decreases. If the sign of the slope were the other way, then it would be an inverse relationship. But I mean, it's just a simple linear relationship. And notice that we only have one independent variable, x. Okay? Both of those are things that we're going to be able to address in future lectures. We're going to be able to talk about nonlinear best fit lines, maybe something like a parabola will be a better fit or something, or we'll see that there's a number of possibilities there. And we'll talk about the fact that there's such a thing as multiple correlation, where you would have more than one independent variable in your statistical model. But this kind of gets us off anyway on the right track of understanding what we mean by a statistical model. We're using past performance of the system to make future forecasts or estimates, or whatever you want to say, of what the changes, of what the dependent variable will be doing. Hey, speaking of independent and dependent variables, let's talk about question 4 real quick. Suppose you have records of cloud cover and power produced by a solar panel. You can see what I'm going on here? You've got like a data set that says, at this weather station near this solar panel, I see how much cloud cover there was, and I also have observations of like how much power was produced by that station over, that solar panel over the course of a day, something like that. If I'm trying to make some predictions here, which of those two random variables is the independent variable? Cloud cover, power produced by the solar panel, or are they both independent variables, or are they both dependent variables? Oh, that's a tough question in some ways. All right, pick your answer for one of the four choices below and move on. Just get some feedback before you move on to question 5.